Hi, I'm Dr. Wu, and this is Calculus-Based Physics 2. Today, we're going to be talking about Coulombs Law and the force between charged particles. Now, we know from our previous experience in high school physics classes or just generally being around in the world that there is some force that exists between charged objects, whether it be dryer sheets and wool sweater or the nucleus and the electrons that go around it. Our goal today is to be able to quantify the force between charged particles. So to start with, what we're going to do is let's just draw some charged particles here. So consider some charge Q1 and some charge Q2, and we'll assume that these are just some positive charges. We'd like to set up an equation that describes what the force is between these two charges. And that equation is what's called Coulombs Law. So what Coulombs Law says is that the force between these two charged particles is going to be equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared times R hat 1, 2. Okay. Now this looks like a whole bunch of symbols that might not mean a whole lot to you at this point, but we're going to go through and talk about what everything means here. So the first part that we can look at is what the left side of the equation is telling us. So this is a force. It's a vector, and we can tell it's a vector because it has this little arrow above it. And this is the force that points from charge 1 to charge 2. So as this equation is written here, this is telling us what force this charge Q1 acts on this charge Q2. Now, moving over to the right side of the equation, we see we have this big constant here, this 1 over 4 pi epsilon naught. We're not going to talk too much about this. This is just a constant based on the units that we work in, the fact that we use seconds in time and meters in distance. But ultimately what this is related to is it's how an electric field propagates in a vacuum. And it's intimately related to the speed of light. We won't, again, talk about that so much here, but we'll talk later in the semester exactly why this epsilon naught is related to the speed of light and why that's actually important. For now, just treat this as some constant. Whenever you do these types of calculations, this is something you'll just carry through. Now, here we're getting to the more important part of the equation. And this is the part that talks about how much charge do I have, this Q1 and Q2. So the force between these two charges is going to be related to how much charge I have here. So if Q1 is very large and Q2 is very large, I have a strong force between them. If these are small, there's going to be a small force between them. The other thing that's important to take into consideration here is the fact that this is Q1 and Q2, not the magnitude of Q1 and the magnitude of Q2. You might have seen this before where you treat these as magnitudes and then later you say, well, I can figure out what the direction of this is based on whether these are going to repel each other because they're like charges or they attract because they're opposite charges. Here, and when we use this equation, we're going to use the amount of charge, and that's going to also incorporate the negative signs that we might have if we have negative charges, but we'll see that a little bit more once we work some examples. The next part is this r squared that we have in the denominator, and so r is just going to be the distance between these two charges. And so what we see is that if these two charges are close to each other, there's going to be a large force between them, and if they're far away from each other, there's going to be a small force between them. The last thing that we have to consider here in this equation is this r hat 1, 2 term that we have here. R hat 1, 2 by definition points from the charge Q1 to the charge Q2. And so we can say that if I'm at Q1 and I want to point at Q2, the direction that is the direction R hat 1, 2. Okay? Now that we've broken down this equation, let's look at an example. So for our example, what we're going to do is we're going to consider some charge Q1 at the origin that has a charge of minus 3Q and a charge Q2 that's at the point AB that has a charge of plus 2Q. Okay, so we want to find what the force is that charge Q1 acts on charge Q2. So to determine this, what we can do is we can start by writing down Coulombs Law. So that's to say that F vector 1, 2 is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared times R hat 1, 2. Okay, now we can pause here now that we have our equation and look at it and ask ourselves, what are the things in this equation that I need to determine in order to evaluate the equation? So looking at it, we know 1 over 4 pi epsilon naught is always going to be just some constant. That's always going to be the same. We need to know what Q1 and Q2 are. Those are actually given here, so I have my Q1 here and my Q2 here. The next thing I need to know is what R is. What is the distance from Q1 to Q2? And the last thing that I need to know is what R hat 1, 2 is. What is the unit vector that points from Q1 to Q2? And so in order to determine these things, what I'm going to do is I'm going to draw some things in here to help us out. So the first thing I'm going to do is I'm going to draw some line that goes from Q1 to Q2. And this line is going to have some length of R. Now, in order to figure out what R is, I can extend some line down here, and we see that we have some triangle, right? Now that we have this triangle, what we can do is we can say that this side is some length of B, this is some length of A. And so in order to find what R is, we can just go back to our old friend Pythagoras and say that R is just going to be equal to the square root of A squared plus B squared. Okay. So that determines R. We know what Q1 and Q2 are. Now the next thing that we need to do is we need to determine what R hat 1, 2 is. So in order to do that, what I'm going to do is I'm going to draw some angle here, right? I'm just going to introduce some angle theta, and I'm going to extend this line. I'm going to extend this line up here and write the same angle theta here. We can see that this is the same via similar triangles, right? So what I'm doing here is I'm drawing what R hat 1, 2 is, right? Because R hat 1, 2 is the unit vector that points from Q1 to Q2. That's just going to be something that points like this. And so I want to draw that into this diagram here. And the way that I typically choose to draw that is just to extend this line and then make a triangle right here. Okay. So in order to figure out what R hat 1, 2 is, we need to realize that it's going to be a little bit in the x direction, right? This is the x direction, this is the y direction. So it has some amount in the x direction and some amount in the y direction. And our task then is to figure out how much of it is in x and how much of it is in y. And so when we look at this, I usually like to say that, well, R hat 1, 2 is going to be some amount in the x direction, in the x direction, plus some amount in the y direction. And then I can look at my figure that I drew, and I can figure out what this sum amount in the x is and what this sum amount in the y is, okay? So looking at this and looking at this triangle that I have here, the portion that's going to be in x is the adjacent side, and that tells me that this is going to be a cosine of theta. The portion that I have in the y direction is going to be the opposite side, and that tells me that this is going to be some sine of theta, okay? Now, we're getting close, but we're not done yet, because I wrote this in terms of this theta that I introduced in the middle of the problem. I didn't tell you what theta was to start with the problem, and so we're going to have to get rid of it. So in order to get rid of it, what we can do is we can go back to the original larger triangle that we have here and ask ourselves, what is cosine and what is sine in terms of the sides of the triangle that we have here? We remember that cosine is going to be the adjacent divided by the hypotenuse, and so this says that this is going to be A over R, right? So this is the adjacent, hypotenuse, adjacent over hypotenuse, x hat, plus the sine of theta. So sine of theta is going to be the opposite over the hypotenuse, and so this is going to be B over R times y hat. So this is what R hat 1, 2 is, okay? So now we have everything that we need, okay? And somebody's texting me right now apparently. So in order to figure out what this force F12 is, all we need to do is we need to plug in everything that we determined here. And so that's to say that this is going to be equal to 1 over 4 pi epsilon naught times Q1 is going to be minus 3Q. Q2 is going to be plus 2Q. R is going to be the square root of A squared plus B squared, where R squared is going to be A squared plus B squared. And then we can plug in our unit vector. So the unit vector is going to be A divided by R. So this is going to be A divided by A squared plus B squared to the 1/2 times x hat. Don't forget your unit vector. It's very important that this is the amount that's in the x direction. And now we'll take care of the part that's going to be in the y direction. So this is going to be B divided by R, which is A squared plus B squared to the 1/2 in the y hat direction. And if we want, we can simplify this a little bit. So what I can see is I have a factor of 2 here that's going to cancel with one of the factors of 2 here. I have this A squared plus B squared to the 1/2. I have A squared plus B squared. So I can actually factor this out. And what I end up seeing, you'll want to check this. So this is going to be minus 3Q squared over 2 epsilon naught times A x hat plus B y hat divided by A squared plus B squared to the 3/2. Okay? And this is what our force F12 is going to be, okay? And that's our answer. So let's take a look at notation here for a second. You see on the left side here, I have some vector sign. So this is an F vector. So on the left side, I have a vector. On the right side, I had better have a vector. And I do, because I have some x hat and y hat here. If my equation was such that I didn't have some x hat and y hat, I know that something's wrong, because I have a vector on the left side and I wouldn't have a vector on the right side. Let's see if this is consistent with our expectations when it comes to like charges repel and opposite charges attract. So we know that we have some minus 3Q here at the origin. We have a plus 2Q here. These are going to be opposite charges. And so what that means is these should attract each other. And what we calculated was what the force that Q1 acts on Q2. Now, what this says is that there's going to be some force that's going to be in the negative x direction and then the negative y direction. Let's see if that gives us what we expect. So that's going to point down like this. And it does indeed give us a force that's consistent with our physical intuition that says that these two charges should attract each other. A natural thing to ask ourselves is what's going to happen if I put another charge here? What happens if I have some Q3 or some Q4 and you add as many charges as you want? Will this rule still work? And the answer is yes, but we're going to have to add another little piece to it in order to understand exactly how to apply it. That piece is what's called the superposition principle. What the superposition principle says is if I want to find the total force on a charge, I just need to add up what the individual forces are from all of the other charges acting on it. Let's see how that works in practice. Now let's consider this example. Here, what we have is some charge Q1 is equal to minus 2Q at the origin. We have a charge Q2 is equal to 2Q at a comma 0, and a charge q3 is equal to minus q at a point 0 comma minus b. What we'd like to do here is find what the force is acting on the charge q1. So in order to do that, first what we can do is we can write down what the superposition principle says. So that says that the force, or the total force, acting on charge q1 is going to be equal to the force that charge 2 acts on q1 plus the force that charge 3 acts on charge 1. Okay, because those are all of the charges that we have in this system. Okay, so now what we can do is we can write down Coulomb's law individually for F21 and for F31 to find what the total force is acting on the charge Q1. Okay, so in order to do that, what we can do to start is we say that F21 is equal to 1 over 4 pi epsilon naught Q2 Q1 divided by R squared, and I'll put another index here, so this is R21, so this is the distance here, times R hat 21, and because I want to work right below this after this, I'll put the other one over here. So this is going to be F31 is going to be equal to 1 over 4 pi epsilon naught Q3 Q1 over R squared 31 R hat 31. Okay? So now, what we can do is we can look at these equations and then again pick off the things that we need to figure out, or the things that we need to resolve. So we know what all the charges are. I tell you what Q3 is, Q1, and what Q2 is. We're going to need to figure out what this R31 is, what this R21 is, what this R hat 31 is, and what this R hat 21 is. So let's start with the R's, not the R hats. The R's are a little bit easier, I think. And that's just going to be the distance from, in this case, charge 2 to charge 1. So that's this distance. So this distance is R21. Okay? That distance we know because we know where this charge 2 is. This R21 is just going to be equal to A. Okay? How about the distance from 3 to 1? Okay, we want to find out what R31 is. So looking at this, what we can see is R31 is going to be this distance, so this is R31, which is just going to be equal to B. So this is going to be equal to B. Now let's look at the unit vectors. So to determine the unit vectors, let's first look at R hat 21. R hat 21 by definition is the unit vector that points from charge Q2 to charge Q1. And so if I'm at Q2, I want to point at Q1, that's going to be a unit vector that points like that. R hat 21 points like that. We can see that if this is the x-axis and this is the y-axis, that this is identically in the negative x direction. So that tells me the R hat 21 is going to be equal to minus x hat. Now the last one that we need to determine is what R hat 31 is going to be. R hat 31 is going to be the unit vector that points from Q3 to Q1, and this is going to be this unit vector, so R hat 31. So it points from here up here. So this is going to be equal to, in this case, this is y hat, right? Because this is just going to be in the positive y direction. And now we have everything that we need to evaluate this. So let's start with our F12. This is going to be equal to 1 over 4 pi epsilon naught. Q2 is going to be 2Q. Q1 is going to be minus 2Q. Got an extra parenthesis there. Divided by the distance, this is going to be A squared times the unit vector, which is going to be in the minus x hat direction. We can simplify this a little bit more, so we can cancel a factor of 4. We get rid of negative sign. And so this is going to be Q squared divided by pi epsilon naught A squared times x hat. So this is what our our F21 is going to be. Okay, and we can do the same thing with our F31. So plugging in Q3, this is going to be, let's first write our 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, times minus Q times minus 2Q divided by the distance squared, so this is going to be B squared, times the unit vector, this is going to be Y hat. Again, we see there's some things that can simplify here. We have negative times a negative, that makes a positive. We have 2 is going to cancel one of the factors of 2 in the denominator, and what we end up seeing is this is going to be Q squared divided by 2 pi epsilon naught B squared times Y hat, and this is F31. And that's it. So we have our F31, we have our F21, and we know that to find the total force, we just add those together. All right, and that's it for this video.